Hello. Yeah. Good evening. So we'll start today. Uh, the class. Um, yeah. Good evening, everyone. So this is the first class of deterministic network calculus. So this is class 1. This will mainly be an introductory class. Introductory class. So it might not uh, be a whole 1 hour class, but it will be something around 40 to 45 minutes of class. Okay. So yeah. So basically, uh, deterministic network calculus, what we are interested in is we are interested in performance evaluation of networks. So how does networks perform when under different conditions? So on a different arrival. So networks here, when I mean networks, I basically mean communication networks where you have different servers, routers, and all in a network, and uh, you have some source and destination. The servers and routers in the network. The main aim of the whole network is to find and send information from the source to the destination in in a way such that the users, the source and destinations requirements are being met. So to know whether the source and destinations requirements are being met, we need to study that how does different arrival characteristics and different service characteristics affect the performance of the network. So that is why what we want to find is we want to find the performance evaluation of networks. So basically this started with Erlang's work. So the basic model or the basic block of any communication system is a queue. So queue is basically uh, a combination of two things. Waiting queue, where you have area where you can wait, and server. So something which helps you process your work that you want to be done and move to the next stuff. So queues are more general than communication systems. So queues, you can basically imagine them in any malls or any shopping malls or any shopping places or any restaurants. Yeah, there are many places you can, or any ticket booking counters. Uh, so there are many ways where you can basically model a queue. So what happens in a queue is you have a long waiting line where you wait for some amount of time, and then you have a server. At the end of the waiting line, you have a server. So you give some task to the server. The server needs to fulfill that task that you are specified for. So basically, if you see, if you take ticket booking counters, right? There you will see that you have an inflow of people. There are many people coming and they want to buy tickets. So at some point of time, 4 or 5 people can come, and there might be a queue of 4 or 5 people. Now the first person who is in the queue, he wants some movies tickets, so he put forth his request to the server, and the server does the task. Now, due to some issues in the server or how the server performs, he might not perform to his utmost capacity for each and every guy. So there'll be randomness involved in it. There is also randomness in the uh, arrivals. The number of people that arrive at the queue to buy the tickets, they are also random. So there are these two are the main randomness that a communication system usually faces. So the arrival traffic and the service traffic. Okay, so yeah, so let me give a brief example of what a queue is. So basically, you have a waiting queue where you can wait, and you have a server, and after the server is done, you can come out. So basically let xt number of people or whatever it is in communication systems. It's basically bits. The basic unit of that transfers the whole network is bits, and bits wait in each of the router or server in a queue so that they can be serviced and sent to the next location that they need to be sent, right? um, in the queue. Okay, and C be the uh, number of the things, the bits or the people or whatever it is, the server can process in a time unit. So when I say in a time unit, it basically implies that I'm using the discrete time measure, discrete time. So my total time is discrete, but generally, usually, real life systems, they need not be a discrete time model. They could be continuous time model. So, but for now, we'll just for the introduction, for understanding what network calculus does, we'll just use the discrete time counterpart. Uh, yeah, so one, two, so on, and t plus one, right? So this is my time axis, and this is whatever axis that I want, I can. Right. So basically now first you need to model arrivals, right? So what are arrivals? So let's say 80. 80 is the amount of data as per communication data or people or hmm, people in restaurant queuing systems or anything entering the system between times t and t plus one. Right. So basically it is he this the amount of people entering in this. So now what we want to know as one of the performance evaluation is how does the number of people waiting in the queue vary with time, right? So if I see that number of people waiting in the queue keeps on increasing as time increases, because server is very slow, it can we can make some intuition that okay, we need to speed up the server processor, we need to add a new server so that there is no the queue that does not build up. So how does this affect the performance evaluation of networks? Is if you have a huge queue buildup, the waiting times of all the packets that are in the queue keeps on increasing because now the server, now any packet which comes at a later time would have to wait for the server to complete all the packets that are before it. Now suppose uh, you knew that mm, queue buildup is very less, so you can comment uh, on the waiting times that each packet or each people has to observe in the queue and say that. So uh, one of the most famous equations which characterizes the evolution of queue length at each time slot is basically the Lindley's equation. What does Lindley's equation say? Lindley's equation says that xt plus 1, the number of people or bits or data waiting in the queue at time slot t plus 1 is max xt minus c comma 0 plus 8. So what does this mean is this is the number of data, amount of data in previous time slot, right? And each time slot c amount of data can be served. So now suppose from t to t plus 1 c amount of data has been served. If xt is greater than c, then xt minus c is positive. Then what happens is in one time slot, if you have served c amount of packet, xt minus c would still remain in the system, right? So in the next slot, the amount of packets that are remain in the system would be xt minus c plus something else. That plus something else we'll talk about later. So this remains in the system. Now suppose if xt is less than c. If xt is less than c, then this means that xt minus c is less than 0. And at that case, the max of xt minus c in 0 becomes 0. But why do I want to make it 0? So the number of packets in the previous slot are less than the total amount that I can serve. So in the next time slot, I'll serve all that is there with me. Yeah, so yeah, so that means that no packets remain in the system. No older packets remain in the system. Because at each time slot, some amount of packets can always come in. And that is just to add the term new packets that have arrived. So this was the first, this is one of the most basic equations for which where you try to come up with performance evaluations for a networks is look at how the queue evolves with respect to time. So this is here this is really basic because I've done it for a discrete time, and also I've assumed that the um, amount of service that we can do at each time period is constant. This c need not be constant. It could be random. Could be random. Um, so there are different variations to this. Like you could take c as a function similar to xt and ctr functions. You can take both to be random, where c is from some distribution, and you get you sample it, and at each time slot you get some number, and that is a number you can serve at each time. Those kinds of stuff. Now, where does this all come into place? If C is random, then you can assume it to be some wireless communication sort of thing where uh, you don't know how the channel is going to be at some point. So you would expect the channel to not be able to serve at most of the times. Uh, so what this does is this allows you to model the service as random and distribution based. So using all this, uh, we see that yeah. So this is basically one of the starting points of how do you performance evaluate a network. So using this equation, what do we mainly get? We get an information on. We get some information on xt. Right. So how the queue length varies and all. Uh, so there are some works in there are some works which follows this line of um, modeling the uh, communication system. So we have Polzig-Kinchain formula. I'll not write down the whole formula. I'll just tell that they say you basically try to find out queue lengths given the service time distribution. So if the service is not, and there are many more assumptions to this, but I'm just giving you an overview. So you have the Polzig-Kinchain formula, which gives you an evolution of queue length um, when you have random service times. Then you have Little's law, where Little's law says that so it is L equal to lambda W, which is very this is for MG1 server. So what does this mean is your arrivals are Markovians, they are memoryless. you have a random service time distribution. That is very general. So no properties. The service has no properties, and there is one server. There is one server. So basically, the arrivals are basically the distribution of this. The distribution of this is if you have M, that means that it is memoryless, right? And if it is G, so G, the second term is a service. So that means the distribution of this is general. If G means it is general. So it could be any distribution, just some distribution F. It just means that there is a distribution F, right? This is the number of servers. So one server similar to uh, the diagram that I've drawn here. Okay. So next little laws. Little law states that. So this is the expected number of amount of data or number of people in the system. This is an expectation, right? Lambda is the expected time between arrivals. So expected time between the arrivals is 1 by lambda. You can call lambda as the arrival rate, right? And W is the expected wait time or expected time spent in the system. So basically, what happens is the why this is important for performance evaluation in networks is you want to decrease the expected time spent in the system. You want people to come quickly and don't waste their time and go away quickly. So this is with respect to restaurants and ticket booking counters and all. But in communication networks, what happens is even there you have the motivation of not decreasing the expected time spent in the system is you want to decrease the delays that happen between when you're sending stuff from stores to destination. So the quicker, the less the wait times in the network, the less the delay that you'll have at each place. So the main motivation is to decrease the expected time spent in the system. And then you have lambda. This lambda is of the arrival rates. There you have no control over. Right. So it is just the arrival rate. The arrival could be anything. But based on the arrival rate, if you know the arrival rate, and if you want, you have an idea of what is the expected waiting time that you want. This expected number of data in the systems is basically XT, expectations of XT, right? So expectation of XT, as you can see here, is a function of C. Now that is the part where you have control over. So if you can vary C, if you can control C, and then if you can control C, uh, yeah, then you can decrease the uh, W as per your. So the control is here. This is the control. This is the input. And this is your desired output. So this is basically where the whole performance evaluation comes into play. So th these are basically all general queuing theory stuff. Right, we have not still got into network calculus and how does network calculus come into play here. But these are mainly queuing theory stuff. I hope you understand like the motivation behind why do we want to evaluate networks and all. Yeah. So okay, so let me give you some more introduction in other works in this net performance evaluation of networks. So uh, other areas in networks and their performance analysis. So you have something known as the mean field theory. And then you have stochastic geometry. And then you have random graphs. These are all their proper. So these are all different fields which span out to um, to places where uh, they have the same motivation to analyze the performance of a networks. So these are they have different modeling properties. They have different motivations, but they fairly start off from the same um, baseline. That is, they want to analyze large networks. So another direction which we are interested in. So we are interested in um, okay, so let me write down the Lindley's equation once again so that it will be clear. Xt plus 1 equal to max xt minus c comma 0 plus 8, right? So we are basically interested in these two elements, right? The max and the plus. Okay, so uh, so why are we interested in this is so um, okay, so there is something known as max plus algebra. Now this is a semi-ring. Okay, so your normal semi-ring is your R plus into. Okay, so you have R plus is a monoid. We will talk about all this later, but what is a monoid, what is a dioid, and so on. And plus is commutative. And we have two more properties which will go later. If a field and two binary operators have these properties, then we call it as a semi-ring, right? So we see that if you have a set which is reals union with minus infinity and max and plus, then you will see that these all properties are satisfied here, right? So the maximalist algebra forms a semi-ring. And the next thing you can do is you can define convolution through this. So you can define convolution and deconvolution using max and plus components of the thing. So what happens is in linear systems, you have this, you have arrivals and you have arrivals and you have the system and you have output, right? So uh, this is basically for linear systems. Basically, you have this convolution operator, um, which you can use and calculate the output. Similarly, what we want to do is we want to make uh, this system, the queuing system, also as a linear model. So now you have a server and you have an arrival, and you want to find some output. This might be a performance metric or the actual departure process, right? So we also want to make this as a convolution between two things so that you get the metric or the divide process. But in your normal algebra of R plus and into the convolution that you generally define here, this system is not linear. but can you make up a new definition of convolution so that the system that you see here becomes linear, and you can apply uh, linear uh, you can apply concepts of linear systems to your queuing networks to make your performance evaluation easy. There'll be some trade-offs. There'll be some trade-offs while applying this, but that is what we are interested in seeing in this course. So this is the motivation of this is the motivation for why we want to do network calculus. So before going into all the math, so in this course, basically, we will talk about all the uh, math behind how to model and stuff. So we'll talk everything about max plus algebra and an offshoot of it of min plus algebra. Right. We'll mostly talk about min plus algebra and also a bit about max plus algebra. We'll show what are semirings, how does max plus algebra and min plus algebra form a semiring, and if you have a semiring, what are the properties that it will define, and if you have a min plus semiring, then how do you define convolution, deconvolution in that? So if you have now functions, so AT and ST, those are your functions. If you have no functions, then how do you um, how can you calculate the convolutions of different functions that are defined in the min plus and max plus algebra? So what we'll try to do is we'll try to re-establish the notions of convolution and deconvolution in the new setting of min plus and max plus semi groups or algebras. Yeah. So mm, that is a topic of interest. So this is the first part of deterministic calculus. So the second part of deterministic calculus, which I'll be taking in the next sem, there we will see. So now we have the base for the linear systems, the min plus and max plus algebra, and the convolution operator, deconvolution operator. In the next system, we'll see about how uh, to use those properties and model them to real life situations of communication networks, and how do you evaluate the performances of different types of communication networks using those properties that we have just seen. Right. Uh, yeah. So before all that, I'll just give a brief view of network calculus. Right. Okay, so this through today's class, this will be just a brief view of what network calculus is and what all type of stuff you might see. So okay, so basically first we'll see is the flow model. So what does a flow model mean? Flow model means that it is the flow of data that is crossing in a given point in network. So how do you model flow? You can model it as instantaneous amount of data that has been crossing a point, or you can model it using a cumulative function. So there are two ways to model this. You can do um, instantaneous amount of data to a network, or you can model it as a cumulative amount of data to network element to a network element. Okay, right. So the min plus algebra, we generally stick with the cumulative amount of data modeling. We don't stick with instantaneous. The instantaneous, we will see some counterparts between instantaneous and cumulative modeling, where in the instantaneous modeling you'll see something known as that. Um, yeah, I'll tell about it later. But for now, we'll consider the cumulative amount of data traffic passing through it. So basically, here again you have two types of modeling. You can model it using A0T or AT. So A0T basically can say that amount of data passing through a network element in the interval 0 to T. Right. AT also is the same, but now to define something of AST, where S is less than or equal to T, you want to define it as AT minus AS. So basically, uh, what we want to define here is so you have S and you have T. You want to know the amount of data that has passed between in this interval S to T. You take the total amount of in A0S and you take the total amount in A0T. You subtract A0T minus A0S. So if you take the assumption that A0T is AT and A0S is AS, then you can write that AS comma T equal to AT minus S, something of this sort. And since it's cumulative and there is no negative amount of traffic that can go through one point. So basically what assumptions we have is A0T. mm, So A is basically a function which goes from R plus cross R plus to um, R plus union 0. So it can be 0 because A0 is 0. Um, and if these both are less than equal to, then it goes to 0. So yeah, and A is not decreasing. So A could remain constant if no arrivals are coming, but can never decrease because once a flow has crossed a network point, it can never cross back. Like physically, it can cross back, but it doesn't make sense. Like in communication, you want to go from a source to destination. You want to just go through a network once. You don't want to go through it twice. If you are going through a network element twice, then that means that you're just looping around in the same place, which will give you more delay. So you don't want that. So basically, when we model cumulative flow of data, we use a function which maps R plus to R plus cross R plus to R plus union 0, and the function is non-decreasing function. We'll talk about uh, all this later. But this is how we model the arrival process in network calculus. We have not yet started the modeling, but yeah, this is how we look at the arrival process when we in network calculus. Okay. So next is the server model. So this so a server model is basically a network element. So you want to model a network element. So you have some um, network element. This is some network element. This could be a router, this could be a server, this could be it could be anything, right? But it does some part in sending packets to its different locations. So you could have a network, so and you could have some arrivals. Some packets need to be sent to this way, some packets need to be sent this way. Mm, yeah. So you want, and this is your network element S. So we'll call it a server or network element. Either of those I'll call. So basically, S is a relation between two cumulative functions. So two cumulative functions. So one is the arrival cumulative function, which I have defined above, and departure cumulative function. t, which I have defined below, right? So the departure cumulative function is similar to the arrival cumulative function. It has the same properties, that it is also a function mapping from r plus cross r plus to r plus union 0, and it is also non-decreasing. But the departures will always be less than the number of arrivals, right? So at a given point of time, so suppose you have till time t, you can't have more departures than the arrivals that have happened. That means that your server is just taking out stuff from making stuff from air and sending out packets. You don't want that. You want the server to only send packets uh, that it has received from someone, right? So, so, so basically, at any point of time, AT, the cumulative amount of arrivals, be greater than or equal to DT. This is for all t belongs to R plus, right? And the common thing is A0 equal to D0 equal to 0. So there are no arrivals at time 0, there are no departures at time 0. If there was a departure at time 0, it would mean that something has arrived before 0, but we don't take the uh, past into account. We want to start afresh while doing the analysis for a server and a flow model. Okay. So next, performance model. So performance bounds. So what do we have now? We have A, we have A and D. So A are the cumulative arrivals. D is the cumulative departures. Right. So what are the sum of the um, performance metrics that we want to find? So maybe we want to find A comma D. So this is the maximum delay between arrival and departure. Right. So this could be a performance bound. So you could want to find the maximum delay that given a cumulative and departure function, you want to find the maximum delay that is between those two. So uh, so here there is a one more assumption that we are following FIFO. So first in first out thing. So you have a server. The server serves the packet which it gets first. Now you can change the scheduling system and calculate different bounds for the same. But I'll be explaining in the today as a first class, I'll be just explaining about FIFO. And in this course, I think we'll just in the first part of the course, we'll just talk about FIFO. We might not even talk about FIFO, we'll talk about the mathematical basics of the network calculus thing. So we'll mainly concentrate on min plus and max plus algebra. We might talk about FIFO in some cases just to give an example, but scheduling part and all will come in the next course that I'll be looking to offer. So basically what you have is you have time and you have data, right? So you'll have some non-decreasing cumulative arrival function A, and you'll have some uh, cumulative non-decreasing departure function. So A is the arrival, this is the cumulative arrival or AT, and this is DT, right? Keep in mind AT is always greater than DT. So suppose I know what time this is, and one packet has arrived here. So I want to know when that packet leaves, right? So to know when the packet leaves, I just need to calculate the horizontal distance between these two uh, curves. So this is the horizontal distance. Now, similarly for, so suppose now I have T prime, right? I want to know when does this packet leave? Packet leaves somewhere. This is the delay that the packet, maximum delay that the packet will absorb, right? Uh, Yeah. So actually no packet has arrived here, but let this be this packet that has arrived here. This will see a maximum delay of this much, right? Deep. So yeah. So now you will get uh, if you know the arrival and the departure processes, both these functions clearly, then you can calculate the delay that each packet would get, the packet which is come at t, each packet would get, and you can calculate a supremum over all this, and you can calculate the maximum horizontal distance between A and B. So basically, what you want to do is, given these two curves, you want to calculate the maximum horizontal between, right? Um, so the exact behavior of the system is always unknown, will be always be unknown, and it will be too complex to handle these curves because you don't know when you have huge number of flows and curves, you don't know when will there will be a flow in the arrivals or the departures. So the main basic principle of network calculus is to abstract the concept of the flow and servers by something known as, so this is important, something known as arrival curves and service curves. Arrival curves and service curves. We want to abstract the flow in the server, right? So for the flows, for the arrival flows, we'll bound the amount of data during any interval by an arrival curve known as alpha. So suppose you have, so what does this mean is, so you have S, you have P plus S, right? So you have AT plus S and you have S. So you will get A T AS comma T plus S in this interval. So this is an, sorry, so this is T and T plus S. So you get A T to T plus S. So this is basically A T to T plus S. So in an interval of T, interval of length S, you are bounded by a function. And so your functions of two variables becomes a function of one variable is less than or equal to alpha S, right? Then you can say that alpha S is basically an arrival curve for the process that you want to model it using the arrival. So symmetrically, what you see is a guarantee on the server. It actually bounds the minimum amount of data that can be processed during any interval. So basically something known as beta S, right? So you had alpha S. This is the arrival curve. Similarly, you have beta S, which is a service curve. So now what happens? So while bounding, so you can't symmetrically use the departure process to bound the server because the server can be sometimes empty. So suppose if it is empty, so dt plus s minus dt, if you blindly bound it using beta s, right? So this could be zero sometimes. Like if you pick these 2 points, this could be zero, right? The lower bounded minimum amount of service. So you need your function to be something which is less than zero, but which doesn't make sense. So uh, However, what we'll do is we will show the relation between D, A, and beta, right? And that relation is basically, so you'll have A is less than or equal to A convolution with alpha. This convolution is in the mean plus algebra, not the regular convolution. And then you'll have D greater than or equal to A convolution beta, where this convolution is also in the mean plus algebra, not the uh, normal convolution that you have. Uh, so now you have a basic idea of how to model mm, flows, how to find performance bounds, and then performance from curves. Now instead of working, so instead of working with A and D, you'll be working with alpha and beta, the arrival and service curves. And then we'll try to find maximum delay, maximum backlog, and these are some of the performance metrics that we're interested in. We'll try to solve. And we'll also see, suppose you have two different servers and you have a flow which goes from multiple. Could we convert this? So similar to linear system stuff. So if you have S1 and S2, could I generate this as S1 convolution with S2? And again, this convolution is in the mean plus algebra, not in the integral algebra. But could I do something like this, where I have a sequence of servers in tandem or in series? Could I um, collapse the whole thing into a single server, which we do in uh, linear systems? And we'll also see if you have one server. So if you have multiple flows, could we model this out as two servers with two flows? Of course, you'll be needing the scheduling policy. So scheduling policies, it will depend on what scheduling policy you're using to go map from here to here. But we'll see how can this be broken up as to. Right. Yeah, and then so now you're just going in more generic cases where you have multiple networks and you have multiple flows. Could we also do analysis of something of this sort? So performance analysis of this flow or any one flow that you're interested in, could we analyze such generic topologies using independence? So basically, this would be the whole course for, this will be the whole background for two courses. So this will be basically deterministic calculus part one, in which I'll cover the mathematical requirements to understand the second part, where we go into the modeling of all these and understanding how to do convolution of service curves, or if you have multiple servers in tandem, could you boil down to a single server? So basically, you want to use the benefits of a linear system analysis and um, use that to find performance bounds on your networks that you have. Something similar to that. So next class also will be basic introduction on basic modeling. So what single server, single flow, what is a server, what is a flow, what all stuff you need to do, and some assumptions which are important for the uh, analysis in the next part. So once we are done with that, and we'll give some basic notations that are done in that will be done in the next class. Then we'll go into min plus summirings and uh, what is known as min plus summirings, or why do we call it a tropical algebra and those stuff. It will be purely math. Yeah. So possibly the next class will be tomorrow, same time, 8 to 9 at the night. Uh, yeah, I'll stop it.